So we left off last time. We were doing calculations involving calorimetry, and so I believe that we left off on this question here. So here, this is a neutralization reaction between hydrochloric acid and sodium hydroxide, and we see a temperature increase, and they're asking us to calculate the approximate heat produced by the reaction. So the first step, of course, would be to write down information that's given to you. So they use 50 mils of a 1 molar hydrochloric acid solution and 50 mils of a 1 molar sodium hydroxide solution. The initial temperature was 22 degrees Celsius. The final temperature was 28.9 degrees Celsius. And so we can quickly calculate the change in temperature, which is the final temperature minus the initial temperature. And when we do that calculation, we get 6.9 for the change in delta T in Celsius. So the question is, what is the heat that's given off by this reaction? So here we have the chemical equation that's given to us, and we're wanting to find the heat of the reaction. So I know the heat of the solution is going to be equal to the mass of the solution times the heat capacity for the solution times the change in temperature. So the mass of the solution, I can calculate that by just adding up the volume for each reactant they gave me, which is hydrochloric acid and sodium hydroxide. Okay, so when I add up the volumes, it's 100 milliliters. Because I have 50 milliliters of each. And then, assuming the density of water, which is 1 gram per milliliter, I can figure the mass of both the reactants is going to be 100 grams. Now, I can do this because, if you look back at my reaction here, it's a 1-to-1 reaction. Okay, so here I need to, the total mass here is going to be equal to the total mass there. So 100 grams is what I'm dealing with here, and I'm going to use the heat capacity for water, which is 4.184 joules per gram per degree Celsius. Okay, and so when I plug in my values here, my delta T is from the delta T calculation previously determined. And then we just multiply the mass times the heat capacity of water times the change in temperature to get the amount of heat given off by the solution, which is 2,900 joules when you basically round using sig figs. So here we have 2 sig figs, which is the least amount given to us. So rounding it to 2 sig figs, we get 2,900 joules. All right, so that's the heat of the solution, but that's not the heat of the reaction. So the heat of the reaction is going to be equal to, basically, it's going to be the same magnitude but opposite sign, okay, here, which is equal to the negative of the heat of the solution. So that means the heat of the reaction is not positive 2,900 joules, but a negative 2,900 joules, which indicates, this sign indicates if it's negative, it's an exothermic reaction. Now, if you remember in your lab that you did last week, you did the same type of reaction, and if you remember, the heat went up, and you see that here as well. So if the heat goes up, it's an exothermic reaction. And so if you forget this part here, if you get a positive value for the heat evolved, that indicates it's an endothermic reaction. So remember to do this last step here to just change the sign at the end in order for it to fit what you're experiencing. So you know it's an exothermic reaction, the heat went up, and so your sign should be negative to correspond to the heat that's given off to the surroundings. All right, so here, let's see, this is just an explanation of that. Okay, what we just calculated. If you want to take a look at the PowerPoint, you know, you're certainly welcome to do that. I'd like to show you guys how I do it by hand, do the calculations by hand, so that way it's explained more instead of just shown to you and not really explained. All right, so here's another example. Here we have a hand warmer. It produces heat on a cold day. If you need to warm up your hands at a football game, for example, you can buy a heat pack. And here, this would just be an exothermic reaction, and you would end up having heat evolved, which would warm up your hands. On the opposite end of that, you have a cold pack, and you probably used cold packs before as well. If you have an injury, for example, you can quickly get some relief by purchasing a cold pack. And cold packs, are made of different types of chemicals. In this example, you're using ammonium nitrate and a bag of water. So you break the bag of water. The water mixes with ammonium nitrate, which is a solid in the pack there. And then the reaction between the two produces a lot of reduces the temperature, and it basically cools off the surroundings. And so you're able to enjoy an instant cold pack in that way. So let's see. We have an example here in your textbook. Let me move on to the textbook here. Let's see. Here's a example 5.6. You're having to calculate again the Q for a reaction, and this is a reaction between ammonium nitrate and water. Okay, and so it gives you the mass for the ammonium nitrate and the mass of the water, and it tells you that temperature decreased by 20.3 degrees. All right, so if we let me go ahead and move here. All right, so this is our given information here: the mass of an ammonium nitrate, mass of the water, our initial and final temperatures. Let's see, is that better? And then we're wanting to know the heat involved. Okay, so we know the formula for heat is mass times heat capacity times the change in temperature. So my mass for my solution is my mass of my ammonium nitrate plus the mass of my water. So I add those things together to get the mass of the solution. And then my change in temperature is my final temperature minus my initial temperature, which is a negative 4.6 degrees, but because the temperature went up. And then I'm sorry, it didn't go up, it went down. Yeah, I said that wrong. Okay, so it went down. Finally, it was 20.3, and initially it was 24.9. So the temperature went down, so I have a negative value there. And the heat capacity of water is 4.184 joules per gram per degree Celsius. So to find the heat of the solution, I'm just going to multiply the masses times the heat capacity for water times my change in temperature. And note that it's a negative value there because the temperature went down. All right, so the heat of the solution then is going to be equal to, when I did my calculation, a negative 1,024.1 joules. All right, so then the heat of the solution is equal to the negative of that of the reaction. And so whenever I change my sign, the magnitude is going to be the same. It's going to be 1,000 joules. 1,000 joules because that's how many sig figs I should have there. And then the positive value for the Q of the reaction, it indicates that it's an endothermic reaction. And if you look back at your temperature change since it went down, you know the temperature of the surroundings went down, so it should be an endothermic reaction. All right, so again, when you look at your signs for your heat, it should correlate to what you're seeing with your temperature change. If your temperature goes up, it should be exothermic. If your temperature goes down, then it should be endothermic, and that's what we see here. All right, so let's go back to our PowerPoint here. So the next section talks about bomb calorimetry. Okay, so bomb calorimetry is used to measure energy produced by reaction that yield large amounts of heat in gaseous products, such as combustion reactions. So, for example, if you want to measure the amount of heat in gasoline, and just, setting something on fire like glucose, you can take glucose and catch it on fire and figure out how much heat is given off by the combustion reaction with glucose burning with oxygen. So, bomb calorimeters are very large, robust, complicated systems, okay, that are submerged in water. So we're going to take a look at a picture of what a bomb calorimeter looks like. They're very large. They're made out of steel, and they're very they're not flimsy at all, like a coffee cup, for example. The energy produced by the reaction is trapped in the bomb and the surrounding water. So that's the idea behind it. So here we have a really fancy picture of a bomb calorimeter, and it looks like it's sort of automated in a way. And so it here's on the left, you see a picture of what it looks like if you were standing and looking at the machine, and in part B it shows you sort of a diagram of all the different components. And so here we see, first of all, you see this big container, and it's filled with water. And then the bomb itself has a little sample cup, and that's where you would put your sample to burn there. And then you have some electrodes there, and the electrodes provide a spark because you have to initiate, the combustion reaction. And then you also have oxygen that is actually allowed to go inside the chamber in order for the combustion reaction to happen. Okay. And of course you have a thermometer there to measure the temperature change in the water before and after the reaction. So there are also different types of calorimeters. There's whole body types of calorimeters that are designed to hold a human being, that you can actually measure their metabolism under different conditions, environmental conditions, health conditions, different types of diets, certain types of diseases like diabetes, how their metabolism has been affected by certain health conditions, that sort of thing. And so when we're talking about whole body calorimeters, and we're talking about researching human disease, for example, or just looking at different types of metabolism, we're going to be talking about calories, term capital C, which is basically referred to as kilocalories on the chemistry side of things. So we're very used to the unit calories, because anytime you buy something at the grocery store, you see a label that's labeled how many calories it has. Here is an example where you can see that for a 1 cup serving of this mac and cheese, it's 250 calories, and then they break it down even further into the number of calories from fat, the total fats, saturated and unsaturated, sodium and cholesterol, and so on. And so we're very familiar with this idea of calories. What's interesting, though, the rest of the world uses kilojoules. So, and that's what we end up seeing a lot when we do our calculations. They're in joules or kilojoules. But 1 calorie that we're familiar with capital C, is equal to 1 kilojoule. All right, so before we talk about enthalpy, we have one more calculation involving bomb calorimetry. And so, let's see here. So example 5.7 in your textbook, we take a look here. it looks like right there. So here we're starting out with 3.12 grams of glucose. It's burned in a bomb calorimeter. The temperature of the calorimeter increases from 23.8 degrees Celsius to 35.6 degrees Celsius. The calorimeter contains 775 grams of water, and the bomb itself has a heat capacity of 893 joules per degree Celsius. So how much heat was produced by the combustion of glucose, of the glucose sample? So here's the information given to us: the mass of the glucose, the different temperature, initial temperature, and the final temperature. Of course, temperature went up. You would expect that during a combustion reaction. And then the delta T, change in the temperature, is going to be 11.8 degrees Celsius. The mass of the water in the bomb, and then the heat capacity of the bomb. All right, so the heat of the solution we have to figure out. So that's going to be equal to the heat of the water plus the heat of the bomb. Okay, so this is like an area where it's a little bit different from the other calculations involving heat, where we just multiply the mass times the heat capacity times the change in temperature. All right, so in this case, it's a bit different. So you're first going to have to determine the heat of the water. So the heat evolved by the water is going to be equal to the mass of the water times the heat capacity of the water times the change in temperature. So the mass of the water was given to us as 775 grams times the heat capacity, which is a constant of 4.184 joules per gram per degree Celsius, times the delta T, the change in the temperature, which is 11.8 degrees Celsius. Okay, so when you do the calculation, you get 38,262.6 joules, which if we round it to 3 sig figs, it's 38,300 joules. All right, so the heat of the bomb is going to be equal to the basically the heat capacity of the bomb calorimeter times the change in temperature. You notice the information they gave us, the units are in joules per degree Celsius. All right, so when I multiply the change in temperature, 11.8 degrees C, the units for degree C are going to cancel out, and I'm left with joules. All right, so I'm left with 10,537.4 joules. Let's you round that to 3 sig figs. That's 10,500 joules. All right, so the heat of my solution is going to be the heat of the water plus the bomb. And so I add these two together to get 48,800 joules. Okay, so that's for the heat of the solution. So the heat of the reaction is the same value with the opposite sign, right? Which is a negative 48,800 joules. We know this reaction should be exothermic. It's a combustion reaction. It's giving off a lot of heat to the surroundings. So we should have a negative value in order to indicate that it's an exothermic reaction. We also can note that by seeing that the temperature has increased. Okay, so when temperature increases, we know heat's being given off to the surroundings, and so the reaction should be exothermic. All right, so going back to our slides here, now we're going to talk about enthalpy. So enthalpy is a way we can basically easily measure heat, okay? And so there's different things we're going to talk about. The first law of thermodynamics. Then we're going to define enthalpy and explain its classification as a state function. And then we're going to write and balance thermochemical equations. And then calculate enthalpy changes for various chemical reactions. And then use Hess's law to compute reaction enthalpies. Now, our next lab actually involves Hess's law. And so we'll get a preview of some of the types of calculations that are involved using Hess's law. All right, so enthalpy. So enthalpy is not going away, okay? It's something that we're going to be talking about a lot even in the next semester if you happen to have to take the second semester of chemistry. So we know thermochemistry is a branch of chemistry dealing with thermodynamics, which is a relationship between heat, work, and other forms of energy transformations that happen during chemical reactions, or it can even happen during physical changes, not just chemical changes. Substances act as reservoirs of energy, meaning that energy can be added to them or removed from them. Okay, and that's true depending, because you think about it, even, most reactions are completed or done in water. And so in that case, sometimes you have to consider that whenever you're dealing with reactions and how energy is moving into the system and out of the system. So energy is stored in a substance when the kinetic energy of its atoms or molecules is raised. So there's a type of energy called internal energy. Okay, so the total of all possible kinds of energy present in a substance is called the internal energy, sometimes symbolized as E, but most of the time you see it's symbolized as a capital U. The relationship between the change in internal energy, heat, and work is summarized in the first law of thermodynamics. So here we see that the change in the internal energy of a system is equal to the heat plus the work of the system. Okay, so now we're going to talk about the signs of each species here, heat and work, and how that relates to some things we already know about heat, for example. We haven't really talked about work yet, but we've talked about heat. All right, so internal energy. Energy can be transported into a system resulting in an increase in internal energy. All right, so our capital U would increase if the system absorbs heat from the surroundings and has a positive heat value. So we know if it has a positive heat value, it's an endothermic reaction. Or the surroundings do work on the system. Okay, we'll talk about that in just a moment, how the surroundings can do work on a system. And then energy can also be transferred out of the system, resulting in a decrease in internal energy. So the system releases heat to the surroundings, and the value for heat is negative. We know that to be true when we see an exothermic reaction. Or the system does work on the surroundings. In that case, the work would have a negative value. All right, so this picture really gives you kind of an idea about the relationship between the internal energy and the heat given off or taken up by the system and the work done by or on the system. So here it says the internal energy of a system can be changed by the heat flow and work. If the heat flows into the system, as you see Kn there, or the work is done on the system, its internal energy increases and you have a positive internal energy. When heat goes into the system, or it's endothermic, or when you have work that's positive and it's done on the system. And then if the heat is flowing out, it's a negative value there. Okay, or when work is done by the system, okay, then you end up having a internal energy that's less than 0. So let's talk about types of works, because we talked about sometimes work can be positive or it can be negative. And so let's talk about details about that. So type of work called expansion work or pressure volume work occurs when a system pushes back the surroundings against a restraining pressure. The surroundings compress the system. Okay, here's an example here. Consider an internal combustion engine. So the system, in this case, would be the gasoline and the oxygen. The surroundings would be the rest of the universe, including the engine. So the reaction is exothermic, so heat is given off to the surroundings, so the value for Q would be negative because it's an exothermic reaction. The reaction pushes pistons out, so the work is done on the surroundings. All right, so the work is done on the surroundings. The work, because the piston is pushed out when the combustion between oxygen and gasoline, that reaction happens. The piston pushes down, and that's what ends up cranking or moving your crankshaft, right, inside your engine. So the internal energy in the system decreases in this case because we have a negative value for our heat and a negative value for our work, because our work is being done on the surroundings. Okay, if you notice here, when we're going out here, so heat is being released out to the surroundings, and also piston is being pushed out. Okay, so work is being done by the system. Okay, and the opposite's true whenever you have positive internal energy. Heat's going in, work is being done on the system instead of by the system. All right, so work is a state function or state variable, and so that means that the state function depends only on the state the system is in and not how the state was reached. So, for example, if you are hiking here to the summit of Mount Kilimanjaro, a state function means that you're just looking at the initial and the final state. Doesn't matter how you got there. So mechanism doesn't matter at all. You're just looking at the before and after, just like temperature. We looked at the temperature before and after. Here, if you're hiking, if you're going straight up the mountain versus taking like a longer, safer, easier but longer route, it doesn't matter because the difference is going to be the same if you're considering the initial versus the final value there. Okay, the distance or the displacement, I guess you would say, would be the same. So for enthalpy, it's a state function, and so it's defined as the sum of a system's internal energy and the mathematical product of its pressure and volume. So enthalpy is equal to the internal energy plus the pressure times the volume. Alright, so enthalpy is also a state function. It doesn't matter how you went about it. It's just looking at basically before and after. It doesn't care what happened in between. Okay. So enthalpy values for specific substances cannot be measured directly. Only enthalpy changes for chemical or physical process can be determined. So again, when you're taking differences here, the path and how you got to that point is irrelevant, because we're just looking at the change in the enthalpy before and after the reaction occurred, not during the reaction. All right, or physical change, whatever that, whatever your case may be. So here, commonly, chemical and physical processes occur at constant pressure. Okay, so when you're in the lab, the pressure is usually constant, and as scientists, you normally don't check on the pressure because it's usually around, it's usually a constant if you're in the same room and, doing experiments in the lab and in a building somewhere. So at constant pressure, the enthalpy change is equal to the change in the internal energy plus the pressure times the change in the volume. So by definition, the arithmetic signs of delta V and W will always be opposite. So The negative value for work is equal to the pressure times the change in the volume. So if we want to go ahead and derive some of these values here. So at constant pressure, Q is equal to QP, that P meaning constant pressure. So the change in the internal energy is equal to the heat given off at constant pressure plus the work. So substituting in the enthalpy change equation yields basically work is equal to work minus work, which cancels out, which means that the enthalpy change is equal to the heat at constant pressure. So chemists usually perform experiments in open container and under normal atmospheric conditions, so the external pressure is constant. At these conditions, if the only work done is caused by expansion or contraction, then the heat flow and the enthalpy change for the process is equal. This makes enthalpy the most convenient choice for determining heat. Because basically, if you can determine the heat amount, you can determine enthalpy, which we actually calculated the other night in our lab.